All right. Now, what do you think? What happens to gas pressure when you raise the temperature if the container can expand in response to the force? What happens to the gas's pressure when you raise the temperature if the container can expand? Now, Jace, I think, answered this one for us. You want to try again, Jace? What happened? What did you say? Or maybe it was Landon. Go for it, Jace.
No,
okay, tell us. What happens to the pressure if the container can expand?
The pressure is just going to stay constant if the container can expand until it reaches a breaking point and the pressure becomes too great.
Okay, so in a rigid wall container, what's happening to the pressure?
You're already at that breaking point, so the pressure, once the temperature begins to rise, so will the pressure, because the volume won't be able to increase to go along with the gas pressure.
All right, very good. So if when we raise the temperature, which is, what did, oh man, I'm forgetting who answered that question. Was it Sarah? No, it was Sarah, yes. Alyssa, what did Sarah say we are doing to the gas when we increase its temperature? What are we doing to it?
We're increasing the motion of the molecules.
That's right. We're increasing the motion. And more motion means that there's more collisions to occur and more force is being exerted on the container. If the container can respond to that by moving out more, then that increase in motion won't actually result in an increase in pressure, right? But if it's a fixed container, then the pressure will increase. Okay, how about this one? Preston? What happens to gas pressure when you increase the number of molecules in the container if the container can expand? Preston?
Pretty much the same thing. If you increase the number of molecules and the container can expand, the pressure will stay the same. If you're increasing the number of molecules in a rigid container, the pressure will increase.
All right, very good. Excellent. Are there any questions about either of those? Okay. You take a balloon underwater. What do you think is going to happen, Aisha?
I'm not sure.
Okay. In terms of the factors that we've talked about, right? N being the moles of the gas, V being the volume of the container, P being the pressure, right? What is changing when we pull something down to the bottom of the ocean? Are we changing the moles of gas in the container? In that balloon? We're not putting more moles of gas inside, right? And we're not decreasing the moles of gas. They're trapped in that balloon. We're just taking the balloon down to the bottom of the ocean. It's changing the pressure, isn't it? What does it do to the pressure of the balloon when we take it down to the bottom of the ocean?
The pressure increases.
The pressure increases on the outside of that balloon, right? So the balloon, it can respond to that pressure. So how is it going to respond? How is the volume going to change?
Does the volume change?
The volume does change. The volume does change. Okay, so how does the volume change? Here's a balloon. I have it right here, right? And you can even try this with a pool at home. It's kind of hard to get that balloon to stay at the bottom of the water. But as you drag this balloon down to the bottom of the ocean or whatever it is, right? Then down here, the balloon is going to be smaller because the water molecules are pushing on this side of the balloon harder than the air molecules were pushing on the balloon up here. That increased pressure on the outside results in these air molecules having a lower relative pressure inside and therefore a smaller volume. Okay, so the balloon will be compressed when it's taken down to the bottom of the underneath the water, bottom of the ocean. All right, so pressure and temperature. We already talked a little bit about this, but as you increase the pressure on a system, then the temperature will increase as well. And that's essentially, I mean, how can we increase the pressure on a system? I think it's easier to think of the other way. The way to increase the pressure of a system is to increase the temperature, the movement of those molecules of gas, right? Here's an interesting scenario. If I have a container of propane gas, right, or butane, is it butane? I can't remember. What's the gas you have when you go camping? I think it's propane, right? If I have a container of propane gas and I have it hooked up to my stove, and let's say I'm cooking, I'm going camping, and I'm cooking some, these are eggs, right? I'm cooking some eggs on my propane stove, right? What happens to that container when I cook those eggs? Anybody have any experience cooking eggs with a propane stove like this when you go camping? Not a single soul, huh?
It gets like once you've been using the propane, the tank actually gets cold, like the bottom of it, where the pressure's decreasing and you're losing it.
That's right. This gets so cold it begins to freeze. Little bits of ice begin to grow on the surface here because it's so cold. So what we've done is we've lowered the pressure. How are we lowering the pressure by cooking eggs? What do you think we're doing? Let's see, whose turn was it? Precious. When we cook eggs with our propane, how is it that we're lowering the pressure?
It's burning the particles inside. So like it's the particles are getting outside.
Very good. The gas is going out and being burned, so there's less molecules, fewer molecules in there. So we're lowering the pressure. And what did we say? Is there a direct relationship between pressure and temperature, or an indirect relationship, Precious? A direct relationship or an indirect?
A direct.
A direct. So as pressure goes down, we should see temperature go down as well, if you have a fixed volume. And that's, those propane tanks can't expand and contract in size, right? Very good. Okay. We can combine pressure, volume, and temperature into a single statement, like this one shown here on the bottom right. Now, if we had a problem where they gave us the change in pressure, volume, and temperature, right, then we could solve that sort of a problem using this combined gas law, pressure, volume, and temperature. Let's try that. We have a question here in the book. Let me get this problem here. 1145. Okay, so let me see here. Okay, a sample of argon has a volume of 6.18 liters, a pressure of 761 torr, and a temperature of 20 degrees Celsius. It's expanded to a volume of 9.45 liters and a pressure of 373 torr. What's its final temperature in degrees Celsius? Okay. Now, after we have the equation, it's just plug and chug, right? It's not hard. And so the relatively hard component is thinking the problem through and identifying what these relationships are in terms of, are they directly proportional or indirectly proportional, and how an equation would be set up for ones that were directly or indirectly proportional. Okay? Try that one more time. Okay? So we have to set it up. Now, we're not going to sneak a peek back at the other slides. We're just going to use our mind and our memory and our experiences in life to pick these out. Let's see, Landon, we want to know, first of all, they start talking about the volume and the pressure. How are volume and pressure related to each other, directly or indirectly, Landon?
Directly.
Directly. So if I have volume and pressure, if I decrease the volume, does that decrease the pressure?
Yeah.
What's that?
No, it increases the pressure. It increases the pressure. They're
Okay.
indirectly.
So these are indirectly, yeah. Now there might have been confusion because that one slide had a bad explanation on it. So this is an indirect relationship, volume and pressure. Okay? So if I have to write volume, it doesn't equal pressure, it equals 1 over pressure, right? So the indirect relationship has to look like this, volume and pressure. This way, in this sort of a statement here, as the volume goes up, so if this volume goes up to a higher value, let's say it goes from 1 to 2, to make this statement equal, whatever this is, let's say it's 10, right? It has to go down here. Does everybody see that? Okay. So when things are indirectly proportional, the relationship V1 P1 equals V2 P2. Very good. Now, the other component is temperature. So, Brielle, what do you think? Is volume and temperature indirectly proportional or directly proportional? Volume and temperature.
Indirectly.
Volume and temperature are indirectly proportional?
Yeah, because temperature and pressure are directly, so that would make volume and temperature indirect.
Let's see if we can figure this out. If I have a balloon, a container, right? Let's see, it was volume and temperature. So we're going to take a balloon and we're going to change the temperature. Here's my balloon. Let's say it's at 1 liter and we're at 20 Kelvin. All right. If I go to 40 Kelvin, what would I expect the volume to do? Whoops, off screen here. 1 liter balloon, Brielle, at 20 Kelvin. I'll put this on there so we can tell it's a balloon. I go up to 40 Kelvin. What do I expect the balloon to do? Increase or decrease in size?
Increase.
That's true, right? We expect the balloon to increase in size. It gets, whoops, I didn't do a very good job. It's just a little bit bigger, but it should be 1 liter. It should be twice as big now, 2 liter, because we doubled the temperature, right? So it shows that as volume goes up, it's easier to think about the temperature. If the temperature goes up, what is the volume supposed to do?
Increase.
What's that?
Increase.
Increase, that's right. So we're not indirectly proportional, we're directly proportional, where volume goes up and, other way around, easier to think about. Temperature goes up, volume goes up as well. Okay, so let's give ourselves a little equation here. What do we have there? We have this example we can still use. 1 liter, 20 Kelvin, 2 liters, 40 Kelvin, right? Can I set it up like this? Volume and temperature, volume and temperature. Is that okay? Is that going to work out for us, Jace? Look at those numbers. Is that setup going to work?
No.
It's not, is it? Right? 1 times 20 does not equal 2 times 40. What do I got to do instead? Volume, whoops, over temperature. Volume over temperature. Does that work out?
20. Yeah, that'll work out.
That does, doesn't it? 1 over 20 is 2 over 40. Okay, very good. So volume and pressure, we saw was like that, but volume and temperature looks like this. So from those two little practices that we did in our head just now, we can regurgitate the combined gas law, which is Vp over T equals Vp over T. Okay? And that's what I'm interested in you guys being able to do. If you can, from your own experiences, sitting down, holding still, thinking about what happens when you take a balloon or a container or a situation of gas, whatever it is you want to think about, and change the pressure, change the temperature, you can regurgitate this. After you have that, again, it's just plug and chug. Okay? Let's see, whose turn is it? Who do we got there? Camille. Looks like it's your turn again, Camille. So you get to plug and chug for us. We identify the combined gas law, V1 P1 T1, or V1 P1 over T1 equals V2 P2 over T2. What do I have for my V1 in this problem here, Camille?
6.18 liters.
6.18. Can you see the initial pressure?
761 torr.
761. How about the initial temperature?
20.
20. Now, can I write the 20 down here, Camille?
No.
I can't. You knew it was no because I asked you, right? Why can't I? Why is it that I have to be careful, Sarah? What do I have to be careful about when I write the 20 down there?
It needs to be in Kelvin.
It needs to be in Kelvin. Now, how do I get to Kelvin from Celsius? Sarah?
Add 273.
Add 273. So I'm going to go 273 plus the 20, and that's going to give me 293. Okay, very good. The rest of that, Camille, do you
I
want
have a question.
Yeah, go ahead.
Why don't we have to change the torr to atmosphere?
Well, if we change this to atmosphere, we would just have to change that to atmosphere. So as long as we're okay, as long as we have the other one in torr, in which they gave us 373 torr, then we don't need to. Whoops, sorry, that's volume. I meant pressure. So 373 is our second pressure, right? What's our second volume? 9.45, right? As long
So
as
it doesn't matter as long as they're the same unit.
That's right. It only matters because there's a linear relationship. The volume expands linearly from 0 to infinity, right? The pressure expands linearly from 0. We never have negative pressures. So Celsius, however, can have negative temperatures, and we need there to be a linear relationship starting at 0 and going to infinity for temperature as well. And so that's why we have to use our Kelvin. Okay, so does anybody have an answer for us? Alyssa? No, Camille. Camille was working on this. Camille, did you get an answer for us?
I am like 5 seconds away from it.
Okay, excellent. While she's doing that, I'd like to remind you how we can remember the 273. Right? Well, you're going to have to remember 273, but how do we remember whether you add it to degrees Celsius or you subtract it from degrees Celsius? Let's see. Preston, do you remember how we can remember whether we take our degrees Celsius and add it or subtract it? How do we remember that?
Are you asking how to convert it to Kelvin? Is that what we were talking about?
So we just were told that you take 273 and you add it to degrees Celsius, and that's going to give us Kelvin, right? But when in the heat of the moment, I've seen plenty of people take degrees Celsius and subtract 273 to get Kelvin. Okay? Or they take, yeah. So how are we going to remember that that one is not the right way?
That's a good question. I've never tried to think of a mnemonic device for that one. Absolute zero, maybe.
Okay, how does absolute zero help us?
So if you subtract 273 from your Celsius, it'll often end up with a negative number. And so we know that in Kelvin, we're going to hit absolute zero before we get to a negative number.
Very good. Very good. So that's how we're going to remember that we never need to, which one we need to do. That's going to remind us, because we can think, okay, let's say it's room temperature, 20 degrees Celsius, 25 degrees Celsius. If I subtract my 273, I'm going to have a negative Kelvin. So that doesn't make sense. So I have to add 273. All right, Camille, did you get it?
Okay, I got it in terms of Kelvin.
Okay.
And I'm really trying to figure it out with the 273.
All right.
I got a negative number, and we just said not to.
What did you get in terms of Kelvin?
219.6014.
219.6 Kelvin. Now, she's concerned how to get this to Celsius. And what did we say? If I have degrees Kelvin to get to Celsius, what do I have to do, Brielle? What did you say? You subtracted 273?
I subtracted
Or Camille?
273.
Sorry, Camille. Yeah, you subtracted 273.
Yeah.
And you got a negative number. Did that concern you?
Well, I got a negative number, and then you said something about you shouldn't get a negative number.
All right. You can have a negative number if it's in what units?
Oh, in Celsius.
In degrees Celsius, right?
Oh.
You can't have a negative number if it's in Kelvin. So it's probably right. Negative 53, is that what you said?
Yeah.
Yeah, that's right. Negative 53 degrees Celsius. Okay, very good. Excellent. So let's get back to learning new stuff. Let's see. Here's a good question for us. Let's see. Aisha, which units must be used in all gas law calculations? Which units have to be used in all gas law calculations? Everybody else try to find the answer too.
Did ATM?
Do we have to use atmospheres? Did we use atmospheres in that last one?
No, we used torr.
We used torr, so torr was okay.
So no specific units as long as they cancel?
That's true in general, but what did we just have a conversation about? One of these in here we couldn't use in our calculation, right?
Oh, Kelvins.
Yeah, you can't use degrees Celsius, right? You have to use, in gas law, you have to use Kelvin. Does that make sense, Aisha?
Yes, it does.
Wonderful. Okay, very good. Now, here's another practice problem. We did a practice problem already, though, so I think we're going to move on through these practice problems. Unless anybody wants to do another one. Anybody want to do another one? Give me a, say yes down below there if you want to do another combined gas law problem. Okay, good. And then we'll move forward. To our favorite well, one more law here, which is always a funny law to me. Avogadro's principle is that as you increase the number of moles, N, of gas, then you increase the volume as well. So the volume of gas is directly proportional to the number of moles of gas in a balloon. And we already mentioned that one. And what that does is it does something special for us when it comes to chemical reactions like this one, where everything is the same, or everything's in the gaseous phase. Everything's in a gaseous phase. Okay? So if I have a chemical reaction like this, where I say 1 mole of nitrogen gas plus 3 moles of hydrogen gas yield 2 moles of ammonia gas. Okay? What's interesting is I can also make this statement now that because there's a relationship between the moles of gas and the volume of gas, I can also make this statement not just in terms of moles, but also in terms of volume. So I can say here 1, and I can use any volume I want, liter of nitrogen gas plus 3 liters of hydrogen gas yields 2 liters of ammonia. Okay? Now the reason I can do that again is because there is this relationship between the volume of a gas and the number of moles in the gas, right? And you can think of a balloon. If I put a half a mole of gas in this balloon, 1/2 of a mole of gas in the balloon, and now I put 1 mole of gas in the balloon, and let's say the volume here is 10 liters. If I put twice as many moles of gas in the balloon, how big is the balloon going to be, Precious?
Could you skip the paper over?
Sorry about that. If I have a half a mole of gas in this balloon and the volume of the balloon's 10 liters, and now I increase the amount of gas in the balloon to 1 mole, what is the volume going to do?
Will it increase?
Yeah, because how did I know it was going to increase? Because I put more gas in it, right? I blew it up more. Or another way to think about it, if I put 1 breath of gas in, then I get a balloon. If I put 2 puffs in, I get 2. I get twice as big. I got one here. Watch this. That's 1. That's 2, right? So, increasing the amount of gas in a balloon increases its volume. Okay? So, because of that, I can make statements like this again. 1 liter of nitrogen gas plus 3 liters of nitrogen gas yields 2 liters of ammonia. Because the stoichiometry here is usually in what? Usually we don't say liters. We usually say what, Landon?
Sorry, could you repeat the question real quick?
So when I'm telling everybody, translating this statement into English, I say 1 watt of nitrogen gas plus 3 watt of nitrogen gas. What do we usually say?
Liters.
Usually we say moles, right? Usually we say 1 mole of nitrogen gas plus 3 moles of hydrogen gas plus 2 moles of ammonia. Why is it that I can say liters?
Yeah.
Why is it that I can now say liters?
Because they are proportional.
That's right, because there's a
They're
direct
directly
relationship. They're directly proportional. Very good.
Yeah.
Now, let's not get too excited about this. Can I say here, here's 1x combining with 2 y's to form 3 z's. Here's a chemical reaction. All right. Landon, is it okay if I say 1 liter of X and 2 liters of Y combines together to form 3 liters of Z? Can I say that?
Yes.
Should have been,
Or
why can't I? I can't say that with this reaction. Why not? What's different, Brielle? Can you see it?
Is it because of the different states that they're in?
That's right. That's right. This relationship between moles of material and its volume is only with moles of gas, right? So only if you're talking about gaseous relationships can you use not just moles in your description of the reaction, you can use liters. So if this was gas and this was liquid and this one is gas, then I could say 1 liter of X combined with excess Y would give us 3 liters of Z. Sorry, what did I say again? 1 liter of X would give it, combined excess this would give us 3 liters of Z. Okay, so because these are both gaseous, then I can relate them in terms of moles, 1 mole of this, 2 moles of that, 3 moles of that, but I also can relate them in terms of liters because of this principle, which is that the moles of gas is directly related to the volume of the gas. Okay? So, let's look at this question now and calculate the answer. What's the volume of ammonia formed when I react 25 liters of hydrogen with excess nitrogen? What's the volume that's formed when I do this? Let's see, who's up? Jace, you want to help us out here? How would we do this? What would we put to the right of our equal sign, Jace?
So our volume is going to be 25 liters.
So we have 25 liters of hydrogen. That's right. That's a good place to start, right? 25 liters of hydrogen. And what are we trying to answer? What do we want over here?
We want to find out the volume of ammonium.
Very good. Volume of ammonia. Okay, so how are we going to convert liters of hydrogen to liters of ammonia?
By using, are we going to use Avogadro's rule and just the fact that the moles are proportional to?
That's right. So what values do I put in here?
It's H2. 2 and then 3.
That's right. 2 liters of ammonia is related to 3 liters of hydrogen gas. So our 25 times 2 divided by 3 will tell us how many liters of ammonia we're going to get. Okay? Now the only reason we could do it that way is because why? Harry, are you ready to answer a question?
Yeah, sure.
Okay, so give me the thumbs up whenever you guys are ready to answer a question so I make sure I don't call on you if you're not ready. But what do you think, Harry? Why was it that I could answer this question with liters where we would usually answer it with moles? Why is it now I could just use that stoichiometry, right? The stoichiometry of 3 here and 2 there. Why is it that I could just use the liters here and not just describe it as moles? Do you know, Harry?
Because they're in their gaseous states.
It's in their gaseous states, and there's this direct relationship between the volume of a gas and the number of moles that it has. Very good. Okay. I don't think we're going to finish this one, but we're going to have a little bit of a conversation about it. Who's up? Camille, it looks like it's your turn. What do you think, Camille? How would we set up this problem? If 125 liters of hydrogen gas reacts with 50 liters of nitrogen, what volume of ammonia can be expected? What would we put to the right of our equal sign? What goes to the right of the equal sign, Camille? Are you there? I can't hear you.
It's not working. I can tell you what she's saying.
All right. You translate for us.
The liters of NH3 goes to the right.
Okay. What do we start with?
What do we start with?
Why don't you help us out, Alyssa?
125 liters of H2.
Okay. And then I go from liters of H2 to liters of NH3.
Is it 3 to 2?
At a 3 to 2 ratio or 2 to 3 ratio.
2 to 3. Very good. Is that how I solve the problem? Anything else? What do you?
Yes, sir.
Do I have to do anything with the 50 liters of nitrogen?
Tell him I don't know.
I don't know. I mean, is it excess? Well, we'd have to find the limiting reagent.
That's right. That's right. It's a limiting reagent problem. So all we really needed to notice is that it's a limiting reagent problem. So we're going to have to perform it twice, right? Once with the liters of hydrogen, and then once with the liters of nitrogen, and find out which one produces the least, and then that one is going to be the volume that we're going to expect. Very good. So the thing to remember here, it's just like the previous problem, but the thing to remember is that when they give you information about two reactants, that's a limiting reagent problem. Excellent. Very good. So hopefully you guys are learning a little bit here about the relationship between gases, volumes, temperatures, pressures. All right. We have one more, bringing it all together, one more crazy gas law called Pervnert. And we'll talk about that next time on Monday. But other than that, there's a few other relationships that we can learn, and we'll talk about them. But we've essentially gathered almost all of the equations, all of the relationships of our gases that we need to. All right, if you have any more questions, you can hang around and ask them. Otherwise, I will see you guys on Monday. All right. Thank you, guys.